Tá me atrasado, então. Pronto, maluca? Liga aí o...
Não, tá tudo ligado.
Okay. Now our next speaker is Jordana Torrico. She's from Federal University of Minas Gerais, and she will talk about ground state and thermodynamic properties of Cu5-NIPA-like molecular nanomagnets. Okay, please, Jordana.
Good afternoon. My name is Jordana. I will present today the work that was done with Professor João Pascal, intitulated by ground state and thermodynamic properties of Cu5-NIPA-like molecular nanomagnetic. I will do a short introduction, then I will present the study of this model and show some results of the general energy spectrum and the phase diagram, ground state phase diagram, its magnetic and thermodynamic properties, the effect, magnetic calorical effect, and finally some final considerations will be made. Okay, the experimental and theoretic studies of molecule and magnetic molecule have been widely investigated in recent decades, as these systems have interesting properties, magnetic and thermodynamics, and they have practical applications such as spintronic, quantum computing, and others. In addition, some of these molecules may exhibit a magnetocalorical effect. Only of this molecule has this chemical compound known as Cu5-NIPA, which was the focus of our work. This system presents a right unusual pentagramic shape of a triangle-based structure with a part of corner sharing the scalene triangle having an hourglass-like geometry. This model can be seen better in this figure, where we have in this full cycle the copper flash ions with spin 1/2, and the A and the B for the two triangle, and this triangle both sharing this common side 3. J1 and J2 and J3 are the exchange interaction. This molecule can be described by this Hamiltonian Heisenberg spin 1/2 Heisenberg Hamiltonian, where we have the interactions, and the B is the external magnetic field. In the Z direction. This molecule has the exchange interaction ferromagnetic, which don't have no frustrated, is a no frustrated molecule. But in this case, we studied the antiferromagnetic interaction, because the J3 are different direction of J1 and J2. And this causes the frustration in this molecule, and the phase diagram and the thermodynamic it's I forgot. It's better for magnetic-alloy effect. And he will has the spectrum energy as a function of the magnetic field, where we have 4 states. One, ferromagnetic, 2 ferromagnetic, but this Fa2 is for spin 1/2, and this is for spin 3/2. One ferromagnetic with spin 5/2, and the 2 states degenerated ferromagnetic states. Okay. In this figure, the figure A, we have all the interaction ferromagnetic, and you can see only 2 phases. The ferromagnetic is red, green, and blue, and one ferromagnetic. And for the other figures in B, C, and D, we have J3 minus 1, and we can see has the degenerated ferromagnetic phase. Here, the time is a triple point. In the figure C, you can see the same degenerated state is squared and is a quadratic point. And here, in this stars, is a kilovolt point. In this figure, we can see the ground state phase diagram for the exchange J2 as a function B. In this first, we have all exchange ferromagnetic, and we can see only 3 phases, ferromagnetic and the ferromagnetic phases. The most interesting case here is in this case for the figure B, when we have J3 equal minus 1, because here we can have 4 phases, one degenerated ferromagnetic phase, 2 ferromagnetic, and 1 ferromagnetic phase. This phase has residual entropy, and at this point, the square and the star has residual entropy. The solid line has only 2 states, and in this dash dot line, it has 3 states in this line. For all results of this work, we consider only this interaction exchange. The others, it's more simple, and this has more results. We studied the thermodynamic and magnetic properties by these quantities of this molecule. And then here we have the magnetization as a function of magnetic field. We can see for 0 temperature has a phase transition, first order phase transition in all figures. And for finite temperature, in B equal to 0, the magnetization was 0. This figure, we can see that it is like the experimental results. Or when you can see here, the magnetization started in 0, and when increase the magnetic field, go to 1/2, and after 3/2. And it's like for our figure here, this figure here. And our result, it's like the experimental data. Other parameter we study was the entropy. Here we have the entropy as a function of the temperature. For high temperature, we can see, and we have all the states, the 32 states. But for the low temperature, we can see we have the residual entropy for logarithm of 2 or of 4 or 3 or 6. And this is good for the magnetic caloric. Here we have the density plot of the entropy. We keeping this in the background of the phase diagram. We can see in the boundaries the phase transition. We have residual entropy, and this phase all has residual entropy. We can see better the entropy in this figure, where he has the density plot of the entropy as a function of magnetic field and the temperature. When these lines of the entropy meeting, it's all near the phase transition or the other phases. Here we can see the entropy is high. Here is 0, but here is logarithm of 2. It's because the degenerated phase. And we made the isothermal change of entropy as a function of temperature. This figure is better for seeing the magnetocaloric effect because it's the change minus change entropy is positive. We have a direct effect magnetocaloric, and if it is negative, we have inverse magnetocaloric. Only here we have the two, direct and inverse magnetocaloric. And he has the change entropy as a function of magnetic field and the temperature. And this figure is for entropy and change entropy, because here we have the direct magnetocaloric and the line down, up again, when you increase the temperature. We can see this figure is near the boundary of the phase transition. Here we have a positive change of the entropy, and the pass for negative and the positive. It's good because it has direct and inverse magnetic molecule in this region. Okay, our conclusions is the NIPA, this Cu5-NIPA molecule can be described by the spin-half Heisenberg model. Our phase diagram has residual entropy. Our magnetization was in accordance with the experimental data, and this system present direct and inverse magnetic effect. Thank you.
Okay, thank you, Jordana, for your nice presentation. Now I would like to ask if there are some questions here. Yeah, Katarina, please. Yes, please.
Jordana, you write there in your energy spectra, triple point, for example. Could you please zoom and show us how you know from energy spectra there will be triple point? Thank you.
This is okay. Here we have two states, degenerated states for different energy, but for this parameter, the energy is equal. And in this point, we have the order is blue state, and the crossing is the phase transition.
So one is degenerate and one is non-degenerate.
Not degenerate. Because this has 2, 3 here, 4 here. Okay, the 5 it's ordered.
Any more questions, please? There are some guys have Google Meet, please. Maybe there are some people.
No.
Interested.
No.
Okay.
Okay.
No more question? Okay, thank you for colleagues for to assisting this event. And tomorrow we'll continue with our next presentation. Thank you, and once again, we will go or continue tomorrow. See you tomorrow. Thank you. Bye. Do we start? Ah.